welcome to another WJEC A level physics question. This one is question 7 from January 2004's PH2 paper, and this is a question about EMFs and internal resistances. First of all, we've got to define EMF, a very common question. We can define it in a few ways, but the basic idea is that it's the amount of chemical energy converted to electrical energy when a unit charge passes through the cell. We can define it in similar ways. We could define it as the total amount of energy provided to the circuit by the cell, but we must make sure that we got the per unit charge or per coulomb in that definition. Next, we've got a car battery made of 6 cells, and each of those cells has got an EMF of 2 volts and an internal resistance of 0.0020 ohms, and they're connected in series. And we've got to write down the internal resistance of the car battery. Well, what we've got is 6 lots of 0.0020, so we've got 0.012 ohms. To start the car, a starter motor is connected across the battery, and a current of 180 amps flows through the battery and the motor, and we've got to calculate the PD across the battery terminals for this current. So here we can use V equals E minus IR given in the data books. We're trying to find V. The EMF for the cell will be 12 volts, 6 lots of 2 volts, minus 180 amps times that total internal resistance of 0.012 ohms. Put that into a calculator, we end up with 9.84 volts, not ohms. For part 3, when doing repairs under the bonnet of a car, it may be safest to remove the battery to prevent accidental short circuits. Suppose a spanner were to be dropped and came to rest bridging the battery terminals. The spanner can be taken to have zero resistance. How large would the current be? Well, here we can just rearrange the standard V equals IR formula to give current is V over R, where R here is going to represent the total voltage and V is going to be the EMF of the cell. It's effectively a rearrangement of the equation above. Not the equation above, it's essentially a rearrangement of this one, E equals I R plus R, which is that the EMF for the cell is the current times the total resistance. So anyway, if we put in the values, the EMF was 12 volts. The total resistance will just be the 0.012 ohms for the internal resistance because there's no external resistance. That will give us an answer of 1000 amps. To calculate the power produced by the battery, well, here we can just simply use P equals IE, which is a special case of P equals I times V. So we've got 1000 amps times the EMF of 12 volts, which will be 12,000 watts or 12 kilowatts. Next, we've got to give a reason why such an accident could be very dangerous. Well, that large current is going to produce a large heating effect. So what could happen, for example, is that the spanner itself could get very hot to the touch, or the acid inside the battery could boil. Lots of different reasons, but it's all to do with the fact that there's going to be a large amount of heat being produced there. Suppose the battery in your car is flat, has run out of energy. A friend who's not studied AS level physics suggests that the battery could be replaced by a number of cells of the type used in torches connected in series. Now each of these cells has an EMF of 1.5 volts and an internal resistance of 0.3 ohms. And we need to explain why the maximum current such an arrangement could possibly supply is 5 amps, no matter how many cells used. Well, the biggest current that we're going to get in the circuit is if there is no external resistance. So let's put that down, assume that there's no external resistance. If you like, we're assuming that the cells are being short-circuited. To calculate the current in the circuit, we would have this calculation. Let little n represent the number of cells. So the total EMF would be N times E. The total internal resistance would be N times R. You can see that those will cancel. The EMF is 1.5. The internal resistance is 0.3. If we divide those, we get the 5 amps suggested in the question. The basic idea is that every time we add an extra cell, we're increasing EMF by 1.5 volts, but we're also increasing the total resistance of the circuit by 0.3 ohms. For part 2, a better idea for starting the car is to use a pair of insulated copper wires, your jump leads, to connect the battery to your battery to a battery in a friend's car. And suppose that each wire is 3 meters long and the voltage drop across each wire is 0.72 volts for a current of 180 amps. And the resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Well, let's first of all work out what the resistance of our jump lead is by taking the 0.72 volts and the current of 180 amps. So I'll just do that on the calculator a second. That will give us 4 times 10 to the minus 3 ohms. Next, we can use the resistivity formula, R equals rho L over A, and rearrange it. A is rho L over R. So put in the figures. Rho is 1.7 times 10 to the minus 8. Length is 3 meters. The resistance is 4 times 10 to the minus 3 ohms. We put those into the calculator. We get an answer of 1.275 times 10 to the minus 5 meters squared. Hence we've got to calculate the diameter of the wire. Well, we know that the area is pi r squared, so r will be the area divided by pi square rooted, and the diameter will be 2 times that. So it's square root of 2 times 1.28 times 10 to the minus 5 over pi, and that will give us just over 4 millimeters, 4.03 millimeters. Of course, you could do this in steps. You could have worked out the radius first and then doubled it to get the diameter. But if we can do calculations in single steps, so long as we show the workings, we can use the answer questions more quickly. Finally, we've got to discuss whether ideally jump lead should be made of wire of larger or smaller diameter. Well, if we go back to the R equals rho L over A formula, we can see that resistance and area are inversely proportional. So what we want is a large diameter, because that will give us a small resistance. And obviously the smaller the resistance, the easier it is to be able to create a nice big current in our charging circuit. So thank you very much for listening. Please remember to like and subscribe, and feel free to add any comments. Goodbye.